Thank you very much, Alan, for the warm welcome and the kind introduction. Good morning, Oregon. Welcome to Chip Wars, Make 'em and Break 'em. This is my first talk for OSU, and this is also my first ever opportunity to start a talk with a quote. So, what's the quote? I'm going to read it to you. They say data is the new oil. If so, maybe advanced chip foundries are the new nukes. 10 years from now, superpower status is going to be defined by the ability to make semiconductors. So that comment was made by Bharat Kapoor by a consulting firm called Kearney. And when I read that, it kind of resonated with me. And I thought about it. Well, I mean, nuke is quite a drastic word, but I think economically speaking, he is absolutely right. But I think what is kind of missing in there is it's not only about making semiconductors, it's also about breaking them. And of course, we're talking about the most recent ones. So how to make them, how to break them, and how to continue to do so in the future. I think that's really interesting and a really important topic. So the outline for my talk is part one. What is the current state of affairs in the chip industry? I will be briefly addressing the ongoing global chip shortage, talking about the complex supply chains and some exciting trends in manufacturing. And then I'll move on to part two, which is about breaking chips and their security. So what is the theory versus the practice? And I'll provide some examples, talk a little bit about some previous research and ongoing research, and also provide an outlook for the next 5 or 10 years or so. So I guess if you have been trying to order chips in the recent past, it was not working out too well for you. So I'm not sure if you know the Digikey lead time trends. This is a screenshot I took just 2 days ago when preparing this talk. And as you can see, this is the semiconductor kind of column from that web page, and you can see the lead time in weeks according to the supplier being mentioned here. So here we see ST Microelectronics, 44 weeks, NXP, almost a year, same as Xilinx, and the trend is even going up. It's not going down. So this is kind of really bad. Everyone is affected by that. So if you're not kind of in the chip business, you still probably heard about that. It's a big topic. And something else that I read is that producing a single computer chip can involve more than 1,000 steps and 70 separate border crossings. So as you can imagine, COVID had a really bad impact on that, and also some kind of internal factors in the chip industry further contributed to that fact that it's such a difficulty now. But also chips are one of the most traded products in the world. I think number one is cars, number two is oil, and number three are actually chips, which is kind of surprising. I would have expected it's something to eat, not our cars and oil and the chips in those cars. So what are the current trends in manufacturing or fab trends? Of course, there's a strong political will for new fabs. It's a big economic factor, and as everyone knows, there is a race for getting smaller and smaller and smaller. Unfortunately, Europe is kind of lost that race already because the most advanced fab in Europe is only at 22 nanometers, so that is the gate width of the transistors. What we're seeing also is, well, since a couple of years, new transistor designs such as thin and gate-all-around transistors. So when I refer to numbers, I didn't want to go into the details too much, so I'm just referring to this as 7-ish nanometers or 5-ish nanometers because the geometry of these transistors kind of keeps on changing. So the US is pretty well off currently, almost at 7 nanometers and having plans for 5 nanometers. Asia is a little bit ahead. And also what's interesting is that the extreme ultraviolet manufacturing equipment needed to go at such small structures is kind of restricted and export controlled. So this is typically what you read about, but I would like to add that, of course, not only the structure size of the transistors matters, but also a couple of other factors, and I will briefly address them on the next couple of slides. So I think if the focus is just too narrow on fabs with only fewer nanometers, I think that's not a good thing, because still the majority of chips is being manufactured in much larger structures than kind of the cutting edge technology we're seeing here. So how is a chip made anyway? So for some of you, this might be boring, so I'll just keep it very brief. A chip is made from a silicon disk, and it's kind of manufactured bottom up. So what we see here is a cross section from an Apple A5X processor. So here in the bottom, this is what we would call kind of the silicon bulk, and then we get into the active region, and then we kind of stack metal on top, layer by layer by layer. So this chip has 5 metal layers, and you can see that when going from bottom to top, the layers increase in thickness, and when we go to the bottom, the layers get thinner. So the overall stack of the chip, so that's the metal and the kind of active layer, is just a few micron. And the bulk silicon not shown here would be typically hundreds of micron. So this is kind of a chip, and I think it's a beautiful piece of mankind that we're able to put something together like this. So once the chip is made, it needs to be packaged, and there are two very common package types. So one is called the wire bond package type, sometimes referred to as spider, because you have this kind of body here, and then legs to the left and to the right. And here, the orientation is kind of upright. So you have the silicon bulk in the bottom and the active region on the top. So that would be the same as shown here in the cross section. And another typical type of integration is the flip chip, where you just turn things upside down. So the active region is now at the bottom and the silicon bulk is at the top. So those are kind of the 2 or 3 basics about how a chip is made and how it's being integrated in a package. So when we talk about smaller structures or smaller transistors, it's probably not surprising to most people to hear that we're kind of approaching a dead end. So there's a kind of theme called more than Moore, which is about scaling effects or scaling trends outside the traditional transistor scaling. And in this case, I would like to talk about improved packaging and integration. So applications often need higher signal integrity, higher integration density, improved power distribution, and a shorter time to market. And one way to achieve that is also 2.5D and 3D integration of chips, as shown here on the right. So this is kind of a scaling diversity, which is not just about the transistors, but other ways to scale and improve the performance and efficiency of a chip. And this has been around for many, many years, but it's now increasingly more common, especially for stacked DRAM for powerful system on chips. Another interesting manufacturing opportunity is the optimization of the power delivery network. So traditional chips, as we've seen before, have signals and power on the top side only. So there is a conflict over resources because we've got signals and the power delivery network. So we need solutions to find other ways to power the chip. So why not just use the backside of a chip? And just recently, 2 ideas have been proposed to do just that. So one is to use buried power rails, and they would be connected from the top, or to use buried power rails in addition to a fully backside power delivery network. So I think this is something really interesting that could help to prolong the life of Moore's law, so to speak, not just by having smaller transistors, but also having kind of other scaling options. I think this is quite promising, but significant manufacturing challenges are ahead to kind of solve this and make a product out of it. So just keep that in mind for a second while I'll move on to the next part of my talk, which is about how to break chips. So when we talk about chip and hardware security, I would like to point out that making chips and especially running a fab is $1 million or $1 billion investment. So it's very, very, very expensive. But how much is breaking the security objectives of a chip? Well, typically it's much less. Of course, we're not interested, at least not always interested in getting everything out of the chip. Sometimes extracting the key is enough or some data. So that could be one security objective to protect this kind of assets. How chips are made is also inherently bound how to break them. So if we put them on silicon and we start building the chip from bottom to top, of course, we just have two sides to attack, the top and the bottom. So aside from the scaling challenge, chips are mostly made the same. So also the fundamentals of the attacks did not change much, especially backside attacks. When we talk about different attacks in hardware security, let me briefly introduce to you the typical classification being used. So one type of attack is called non-invasive. That is when we are not allowed to modify the chip, but instead we kind of just observe it. So one way could be measuring the electromagnetic or photonic emission of that chip. In the semi-invasive case, we're allowed to do more to the chip, such as fault injection, where we provide some voltage outside the typical limits used for that chip, which is then called a voltage glitch or a laser. So that can introduce faults limited to a certain amount of time. And by doing so, we can, as an attacker, achieve our goals. And then there are also fully invasive attacks. Some of them are delayering, microprobing, or reverse engineering. So in that case, we're allowed to fully take the chip apart. Delayering means the stack that we've seen before is now layer by layer removed and then studied to extract the secrets or the functionality of that circuit. So one example that has been recently presented in a paper is called a side journey to Titan, which is the Google two-factor authentication security key shown here to the right. What the authors demonstrated was a successful key extraction by means of electromagnetic side channel analysis, which was kind of surprising because it was a certified chip and the assurance level of that certification was 5+, which is not too bad. Side channels have been around for 20 years plus, and many countermeasures have been proposed and also been used in that chip, but still the authors managed to extract the secret from that chip with a hardware setup with a cost of just $14,000. So, and at the cost basically for such a setup didn't change much over the years. So certified just means developed and reasonably tested with security in mind, but of course it's not a 100% guarantee that nothing is going to happen. So perhaps I forgot to say this is the chip and this is the probe used to measure the electromagnetic field of that chip while it's running. So let's have a look at another example, which is about fault injection or voltage glitching. This is another very, very recent paper from this year, and it's about the NVIDIA Tegra X2 system on chip. Here, the goal was to unlock some kind of secret or hidden debugging bootloader. And what the authors did is kind of a well-known technique, which has been around for 20 years. They used a transistor as what is called a crowbar circuit. So they connected the voltage going into the chip and the other leg of the transistor, they connected to ground. And then at a certain point, they provide an input, which here is called the glitch input. And by doing so, they glitch the circuit because for a very brief amount of time, they pull down VCC to ground. And then if you're lucky, the system on chip perhaps skips an instruction. And the cost for that transistor is kind of ridiculously low, way below than $1. So with that and some other tools you typically have in a lab, it's possible to bypass the security of that chip. So, and this is not a kind of one-off. It just happened now, and it never happened before. Instead, there was a similar attack presented for a mobile phone SoC in 2020. And the same type of attack also works on many other unprotected chips. So of course, the question here is, if there is no protection against it, does it even make sense to count this as an attack? So in the security certification domain, this would not be counted as an attack, but generally it is. So what do we learn from these types of attacks? So first of all, physical proximity and unobstructed access is always essential for these kinds of attack. Also, what is kind of a surprise is that timely adoption of countermeasures apparently is difficult. So perhaps it's a missing business case or some patents are in the way. The exact reasons we don't know for each and every case we're being presented. And also what is quite striking here is the imbalance of scales. So we have a macro scale attack on a micro scale structure, which is the chip. So for the attackers, it was not even necessary to study the logic of that chip. Instead, it was okay just to observe the electromagnetic emanation or to tamper with the supply voltage of the chip. So how about fully invasive attacks? Well, let's just focus on one thing, and that is cryptographic key storage, because of course, the crypto keys are one of the most important assets in a chip. And I will introduce you to a security primitive for secure key storage that does not use a lot of chip resources. It can be modeled as a function, so it's kind of formally secure, and it provides a key without storing it. But as always, I should provide a cautionary note. If something sounds too good to be true, it probably is. So let's find out. So one big topic in hardware security in the past couple of years have been physical unclonable functions. So what is a puff? A puff could be your fingerprint, and you apply some input, and then you get some output. So we look at our fingerprint, and the kind of random response that we get is the image of our fingerprint. So we assume this has two very important properties. So first of all, it's easy to evaluate and hard to predict. And this basic principle applies to almost every physical object that we have if we look at it precisely enough. So people thought about how to use this in a chip to make it more secure. Now, if we look at a chip, we typically have some arithmetic logic unit and some memory. So in many cases, the memory is SRAM. So this is volatile memory. And if we power up the chip, it's non-initialized SRAM. And in that case, in this SRAM, we have some kind of fingerprint due to the imbalance of the inverters used in the SRAM cell. So if we read out that SRAM, we have kind of a fingerprint, but it's noisy. So to overcome the noise in that binary response, we can use error correcting codes. So now we can store a key inside the chip without actually storing it, because when the chip is powered off, there is no key. And if we power on the chip, we read that fingerprint out of the SRAM. So the advantage is that there is one physical attack that no longer works, which is delayering. So we can no longer optically inspect the details of the circuit. But one disadvantage is that we need some error corrected code. So thus far, it sounds reasonably okay. But what about other physical attacks, such as invasive probing? So we still have our chip, we have our SRAM here, we have some other part of the circuit here. So what happens if the fingerprint data moves through our circuit? Then of course we can probe it. So it was never claimed and not designed to resist this kind of attack, yet there are many papers out there that kind of assume physical unclonable functions are resistant to physical attacks. In most cases, that's not true, and in some cases, using a puff even introduces new weaknesses, such as side channels. So the question still is, and that's kind of a research question here, is it possible to make this better? Yes, there is, and that is called a tamper evident puff. So now we make the fingerprint in our chip kind of really big. And now if we would start to invasively probe that chip, we destroy part of that puff. And this would in turn cause the key derivation to fail. There are some underlying assumptions here, such as that the puff encloses the system. It is, of course, sensitive to tampering, and it needs to protect itself too. So this is a very, very challenging thing to do because we need to consider all types of attacks, whether they are non-invasive, semi-invasive, or fully invasive. And still we want that property that the fingerprint kind of surrounds the chip. And the question is this actually possible? And what if we could do this on a chip package or enclosure level? So some of my
Vincent,
previous, yes?
you have a question in the chat window on a puff.
Oh, sorry, I didn't see that. You're assuming that non-written SRAM will power up in the same way each time. No, the bits in that SRAM will be different each and every time. That's what I was referring to by saying it's a noisy response. So that's why we need the error correction code, because let's say 70% of the bits will be the same, but 30 bits will change each and every time we power up the chip. Sorry, I didn't see the chat window because I had this window popping up saying I was being recorded. So some of the previous research that I did, and it's still ongoing research, is to think about some kind of puff enclosure. So not some part of the circuit in the chip, but having some large scale structure. And this would be made from a fabric that carries puff properties. So we could measure them from the inside, get some measurement data, run our error correcting codes, and get a fingerprint. And with that fingerprint, we could detect if someone was trying to penetrate that physical boundary. Because if the physical boundary would be penetrated, then the fingerprint would change. So this is not necessarily about key storage. It's about detecting physical tampering with the board or the chip, which is why this is called anti-tamper enclosure. So this is the basic idea. And I think no one has been able to do this yet, but research needs to be done to get to this point. And this is, of course, something I would like to investigate in the future, aside from other topics. So I will move on to the conclusion, which is only the first part. So chip manufacturing is likely getting more diverse technology-wise. So just scaling the transistors, I think, is not going to cut it in the future. And we've been seeing this development already in recent years, that we see 3D integrated packages and work being done or research to improve the power efficiency of chips. If we could use this for security, and if we do this right, we could get more security out of it. But if we don't pay attention, we may also see the return of some old attacks again. Unfortunately, I think attacks in general are getting way too much attention. So the kind of security fails draw a lot of attention, while some of the reasonably good countermeasures don't get any attention at all, which is kind of sad. Then when talking about the manufacturing cost of most recent chips and making that kind of billion-dollar investment to have the latest fab. The question is this really worth it? Because you could be still an attacker having the capability to analyze them. So when talking about the most recent chips and manufacturing them, I think we should definitely be talking about how to manufacture them and do so securely, such that during the whole lifetime of that chip, it stays secure. And also, perhaps not every answer to today's problem is inside the chip. Since the chip manufacturing process is so complex, inventing new security primitives is really difficult because you're basically not allowed to change anything. And also, just as a side note here, of course, criminals sometimes make use of chips as well. So not just as part of, let's say, using a phone, but as part of deliberately creating a gadget to, well, whatever they up to. So there are also lawful purposes that make it necessary to hack into chips. So security always comes at a price, and I think so does vulnerability disclosure too. So the price could be actual dollars being paid or some vulnerability being lost as part of, let's say, a lawful purpose. So this is kind of a gray area, and especially in the hardware domain, I think this has not been, let's say, addressed adequately. Also, I don't think that the time of silicon-based chips is not over yet. First of all, many chips are still being manufactured in much larger technology nodes, so not the bleeding edge technology we're seeing in our phones. So I think silicon chips will be around for a very, very long time. And even for the most advanced nodes, I don't see any, well, not any problem, but let's say for the next 5 or 7 years or so, I think there are still plans to make it happen. Also, what I would like to mention is that the hardware world works completely different to the software world. So one reason for that is longevity commitments made by the manufacturers that contradict a timely remedy just in case a security issue is being found. Another one is that the expected lifetime in the field can be up to 20 years or even more, which is not a surprise because when we buy a car, we expect it to last many years to come. So chips are in the field for many years, and I think to a certain degree we have to account for that. So when we create a product or when we do research and we find an issue at the silicon level, we should be aware there is no patch possible. And of course, we can't burden the companies to always do a product recall. Some additional ecosystem problems are that, well, there's a lot going on in the, let's say, RISC-V domain and generally about open designs and open hardware. But I don't think that it is necessarily a solution because the design files still need to be transferred to a manufacturer. So it still needs to be manufactured somewhere. And then you have little to no control about that, which is kind of comparable to having some source code and having it compiled by a compiler you don't know and you don't trust. And also, the disclosure process and the bug bounty programs are not really adapted to the hardware world. So the kind of final question being stated here is how to develop more fundamentally secure primitives. And that, of course, is something I would like to investigate as part of my research. With that, I would like to conclude my talk and make one small event announcement, which is about a NATO STO workshop. So that's the Science and Technology Organization of NATO. It's a research workshop on anti-tamper protective systems for NATO operations, taking place online from the 8th to 10th of November. Please note that registration closes 2 weeks before the event, and also note that the workshop is only open to NATO nations, Australia, Finland, Japan, and Sweden. So if you're outside of that, unfortunately, it's not possible to participate in that workshop. And with that, I would like to thank you for your attention. So if you have any more questions, I'm happy to answer them.
Yeah, thanks a lot. That was very interesting, Vincent. And so, yeah, feel free to ask questions now. I see Marcus has a question. I know we tested your voice earlier. Would you just like to go ask it yourself?
Sure. Just getting back to semiconductor capacity in your research, is it more exacerbated by the ASML problem, or is it more really just a customs problem that we're not going to be able to get through because ASML is going to be back on track Q2 of 2022?
Well, I think IBM and Intel have been teaming up about the 2 nanometers process. So I'm not sure what kind of equipment they're using, but at least what I read about it is that they expect to be back on track for the process that Intel is running, or at least there is hope.
I was talking more about like Infineon, providing 80% of the car parts in Europe. That's one of the problems is the $1 chip due to the ASML tool availability, and Applied not being able to qualify anything below 9 nanometers in that space.
Well, I'm actually unaware that Infineon is running 9 nanometers anywhere in the EU. So that must be a kind of research project or research chip. I think as I said, the most advanced fab I think in Europe is 22 nanometers on, let's say, an industrial level. So if you have a source about that, I would be interested to have that confirmation they're actually running 9 nanometers in Europe.
Yeah, I just emailed somebody. I can forward it to you.
Yeah. So if you do have any questions, feel free to just unmute and ask. Yeah, I was curious myself about how you see the interaction of everything you've talked about with communications as well, because that's going to be just as important. Optical, how should we think about that? The whole, communications and computation together in a security framework.
I'm not sure if I understand your question correctly. Is this about making a chip that does all these functions, or is it about how to communicate the security of a chip to other people?
Well, when we have big enough systems, multiple chips, you're going to have communication networks involving optical. And what are the security concerns there? So you were focused mostly on the internals of chips in this talk, but how should we think about the interconnections of multiple chips, even over wired networks?
Okay, so well, there are different layers to that. So first of all, you have the physical layer and let's say the protocol layer. So I think for many applications, it's sufficient to rely on a good protocol stack. So let's say there is some communication link using TLS. It's a very well-tested protocol, and if there is, let's say, no specific need to develop something new, I would always recommend to just use that. Of course, there is also research on the physical layer, such as, let's say, distance bounding or, let's say, puff-like concepts where you use the channel properties to derive for each party of the communication link some parameters that you can use to establish a symmetric key. The problem with that typically is that you lack the entity authentication part of it. So you can establish a key, but you don't know what the other party actually is because you don't have the entity authentication. So I think there are a couple of problems that still need to be solved on that level to have kind of a physically connected and secure communication.
Thanks. Do we have any other questions from the audience?
Hey, Vincent. Hi, this is Sibin.
Hi,
Hi.
Sibin.
Hi. So in your early part of your talk, you mentioned the fact, the side channel attacks, right? Like, so you said that the electromagnetic based attack did not need them to have knowledge about the logic of the chip.
Well, they knew it's elliptic curve cryptography they're attacking, but they did not need to know the specifics of the implementation, which I think is great for the attacker because you can observe the emanation on your scope and just kind of deduce, okay, what is going on? And in many cases, that is possible without knowing the specifics of the implementation. So you don't need to reverse engineer the circuit to perform that kind of attack.
I see. No, I mean, like I said, my knowledge about EM-based attacks is maybe a bit dated, but I remember back in the day, they needed to know, for instance, how many adds and how many multiplies are taking place, and that would be evident from the EM emanations, right? So is that something similar, or has that changed since then?
Well, it's always possible to make an educated guess. I mean, you know what the chip needs to compute, and there are kind of only 4 or 5 ways to do it. So
I see. Okay, fascinating. Thanks.
I do have a question related to your you can't patch silicon comment, which was an interesting way of putting it. So we have all sorts of hardware, important hardware already in the world, and we're not going to be replacing a lot of it immediately. So is there anything we can do to help, keep us secure when there's just old hardware that's not going to get the advanced techniques that you might be developing?
I think you're addressing a very, very good and important point here. So I think everyone is hoping for having some kind of magic box or a sticker that you could put on and it makes it more secure, which is, I think, another great benefit of anti-tamper enclosures, because you separate the development of the chip industry from your security mechanism. So if you have these two separated, it would be possible to use an old chip and just put it in a box, so to speak, and thereby it would make it more secure. Of course, this does not help systems that are being already deployed all over the world. So once they're in the field, I think it's really difficult to come up with something good.
Well, to follow up on that question, though, I mean, would this be not the killer application for FPGA type device or a hybrid of FPGA, knowing the vulnerability that security you might need to change?
Well, even for an FPGA, you have the basic fabric that you can't change. So while you can reconfigure the logic that's implemented by that fabric, you can't change the fundamentals of that chip. So if there is an attacker performing a backside attack, the logic implemented in the FPGA can't prevent that from happening.
Is it possible to detect that you're being attacked, like for a variety of these attacks, or maybe it's impossible? EM attack.
Well, sensors have been proposed to detect the presence of an electromagnetic probe. And also sensors have been proposed to detect lasers or other conditions you typically would like to avoid. But it's still a sensor after all. So over time, by let's say profiling the device, you can possibly work around those sensors. Of course, it's another line of defense. So in general, that's a good thing.
All right. Do we have any other questions from the audience? I always like to have a fun question at the end, so I just want to get any other curiosities cleared
I
up.
have a good question. Hello?
Please go ahead.
Okay. Hi. Thank you very much for this presentation. If, at least on memory chips, I think they have extra rows and columns for what they call repairs. If somebody was able to maybe put unique different silicon logic in maybe some of the extra repairs, because they don't use all of them, maybe this could give us kind of an option B. I don't know, just a thought. I don't know too much about this industry at all.
It's a very nice idea, but which might work in some cases. But I think since the fundamentals how chips are made, so you have the silicon, and then you start kind of putting the active layer and the metal on top. So I think for as long as you don't change the fundamentals of how a chip is made, the attacks will be successful.
Okay, and I guess the second, it's kind of an out there question, but if more countries move to space and there's going to be like neutrons and stuff to have to deal with, maybe they will affect our ICs as we go up. Will there be protection for something like that from like radiation from space?
Well, everything going up to space is going to be radiation tested, or red heart components. I think that's what they're called. They're really, really expensive. So one chip being part of such tests can cost 100K easily. So they do that already to kind of account for the time this component stays up in space, because during that time it starts accumulating the radiation. So I think for space programs, there are kind of procedures in place to test all of that very, very thoroughly.
All right, thank you for your answers.
Sure.
All right. My Zoom is messed up.
We can still see you and hear you well.
Oh, you can hear me. Okay. Because yeah, my Zoom's messed up. So I'll just ask my last question, and I may be lost in cyberspace here. So yeah, one of the beautiful things about computer security is seeing the ingenuity of the attackers. I think you see some really clever folks and clever attacks, and so I thought it would be interesting to hear if you had to pick your favorite hardware attack that you've seen, one that surprised you and you found beautiful, what would you say it is? And maybe say just briefly a little bit about it, not the details.
Well, that's a difficult one because I like them all.
You had to pick a favorite child.
Yeah, I think one of the really beautiful attacks are linear code extraction. That is when you put the processor by means of focused ion beam edits in a state where it just runs through the whole program and you're able to dump the firmware. I think that that has quite a beauty to it because it repurposes a lot of the circuitry that's inside the chip and does a lot of the work for you, such as kind of descrambling the ROM contents and such. I think it's a very tricky attack, and therefore I like it.
Well, thanks. Yeah, those always amaze me. I mean, they always seem impossible, but people pull them off. Well, thanks a lot. This was a great talk, and it was great to learn about your interests. And people can find your contact easily if they're interested in following up. But
yes,
yeah, thanks again.
I don't have an OSU address yet, I think. At least I'm not sure about that. So once I start in December, people can contact me using my OSU address. And until then, they can just find me on LinkedIn.
Mm-hmm. Yep, do a Google search. His name will show up high up. So yeah, thanks everybody for attending. We'll be back in 2 weeks with our next new face in ECS. Thank you.